Well, thanks a lot for the invitation. Yeah, so I'll get started. I'm talking about a particular paper, even a particular piece of a paper. Sounds like some people have read the paper, I now understand. So maybe some will be bored. On the other hand, other people have not read the papers. But at any rate, if I'm going too slowly, you can tell me to speed up. We can talk about other things. Okay, well, I want to start with some motivation and some questions. So I've been interested in this particular group for a little while now. This is this group homeo sub zero. So it's the group of area and orientation preserving homeomorphisms of the two sphere. So again, just to emphasize, a lot of the intricacies of the questions come from the fact that these are homeomorphisms rather than diffeomorphisms. So what I mean by an area preserving homeomorphism is, you give me some open set, then I apply my homeomorphism. Its area is the same as where it goes after I apply my homeomorphism for every open set. And that gives me a group. And it turns out that the structure of this group is a big mystery, just as abstract algebraic structure. So for example, in the 70s, Fati asked if this group is simple. And we figured this out a couple of years ago, or about 2 years ago. However, so we showed that it's not simple. However, there's lots of things that one would like to understand about this group that they still do not. I mean, okay, so it's not simple. That means it has some normal subgroups, but we don't understand the normal subgroup structure so well. As I said, I'll give an example of something else we don't understand very well. It seems to be a big mystery. And also in terms of motivation, let me say that you can ask the same question for any surface. And it seems to be rather mysterious for any surface. And the sphere case seems like a pretty good model for the general surface case. On the other hand, if you haven't seen talks about this, one reason that people were quite interested in the case of surfaces is that if you ask the analogous question in higher dimensions, a lot is known. And actually the algebraic structure is not only completely understood, but it's quite simple. So by that I mean, say I look at volume preserving homeomorphisms of the n sphere in dimension greater than 2, then for example, that actually is a simple group. And that was shown by Fati in the 70s. So the two-dimensional case seems to be quite radically different from the higher dimensional case, at least as far as volume preserving homeomorphisms are concerned. Yeah?
Is the same thing true for like Hamio? So like if I look at Hamio of a higher dimensional thing, so the C0 closure, Hamiltonian.
Yeah, so that's actually quite wide open.
Okay, great.
Yeah, right. So that's a great question. It could depend on what you call the analog of this in higher dimensions. Yeah. So you could ask about the C0 closure of Hamiltonian diffeomorphisms in higher dimensions. You could look, the group of symplectic homeomorphisms. And the structure of that is also quite open. As far as volume preserving geometry goes, which was a kind of classical subject that was particularly popular in the 70s or in the 80s, this has been like a big mystery for those folks. Okay, so any more questions? Okay, so anyway, so you have some group and okay, you want to study it, well, you'd like some invariants. So here's a very interesting potential source that I've been thinking about recently, so-called quasimorphisms. Okay, so what's a quasimorphism on a group? Well, it's almost a homomorphism. In other words, it's a map to R. Well, it's almost a homomorphism to R. It's a map to R such that if I look at the difference between f of A times B and f of A plus f of B, then that difference is uniformly bounded by some constant. So, maybe there are some interesting quasimorphisms on this group that you could use to elucidate the algebraic structure. This question, more or less, had attracted a lot of interest. I'll say what I mean by more or less. But okay, so I'm going to first state the question. So this could be useful, but you could ask, does this actually have any quasimorphisms? And as I said, this had attracted some interest. I guess it sort of goes back to work of Entov, Polterovich, and P, and Gies, and McDuff and Salomon. They had this list of open problems in symplectic topology, and this is more or less problem 23. I say more or less because they state it slightly differently. Anyways, we do answer exactly what problem 23 is as stated, but I want to state it this way because this is a little closer to my perspective. Okay, so does this have any quasimorphisms? Okay, so yeah, so now I can state the theorem. This is joint work with Vincent Humilière, Chuck-Yuma, Soban Seyfaddini, and Ivan Smith. Yeah, so not only does it have quasimorphisms, it has an infinite dimensional space of quasimorphisms. And they're homogeneous as well. So homogeneous means that if I take f of a to the m, then that's just m times f of a. Great. So so that's the theorem. Are there any questions about the theorem or anything?
Is it, do you model out honest morphisms to R here, or?
You mean like homomorphisms?
Yeah.
No, but it's not known whether this group has any homomorphisms at all. But right, so we just construct. So this forms a vector space. You know, you can add two quasimorphisms, etc. Yeah, so it forms a vector space, and that vector space is dimensional. So, okay, so I promised you that you could use these things to better understand the structure of this group. Let me give you an example. So this is a kind of classic example of quasimorphisms, which is pretty interesting, is understanding the commutator length on this group. So let me just give you a review of commutator length. So say I have a group, then I can look at the subgroup generated by commutators. It's actually a normal subgroup called the commutator subgroup. And now if I have something in the commutator subgroup, I can look at the minimum number of commutators required to write it, and that's called the commutator length. So to get a feel for why this might be interesting, there's a nice example from Caligari. Caligari has written like a 400-page book that's just called SCL. The S stands for stable. We'll get to the stable commutator length, but he has a whole book on these commutator lengths. Okay, so what's Caligari's example? Well, for example, this should say pi 1. Say my group was the fundamental group of some topological space, or of some manifold. So say it was the fundamental group of some manifold, and I took an element that's represented by a homologically trivial element. So it's the boundary of some surface, and its commutator length is exactly the minimal genus of a surface that bounds it. Caligari has a nice phrase about this, which you can think of the commutator length as like a group theory analog of the genus. So the question would be sort of, what is the genus of this group of homomorphisms? Yeah.
So in one direction, if you have a surface bounding gamma, then you can write the boundary as a whatever bunch of commutators just coming from the loops on that surface.
Right. Yeah, that's sort of the point. Yeah. And the most efficient way to do that is just going to be captured by the most efficient way to write this as a product. Okay, so how does this work for the kind of groups that we're interested in? Well, here's an interesting example. So say I didn't look at area preserving homeomorphisms. Say I just look at just homomorphisms without any kind of condition. So then it's the theorem of Tsuboi that the commutator length is actually just 1. So it turns out that this group is perfect. It's equal to its own commutator subgroup. And in fact, if I have an element here, then I can write it as just a single commutator. On the other hand, just to give you some idea that this can be rather strange, a more recent result says that if I look at the same thing, but for a surface of higher genus, then the commutator length is actually unbounded. So this group, if you like this idea of the commutator length being a substitute for the algebraic genus, this group has infinite genus. Okay, so what do we learn? Well, we learn from the existence of our quasimorphisms that the commutator length is unbounded. So our group has, again, sort of infinite genus. And okay, so how to see this from the existence of our quasimorphisms? Well, it's easy. So I claim that one can see this directly from the existence of a single homogeneous quasimorphism. So say I have a non-trivial homogeneous quasimorphism. So let's let F be non-zero and homogeneous. Okay, so it's an easy calculation that F has to vanish on a commutator. So if I have some commutator, then it has to vanish on all commutators. So on the other hand, so if I have a product of n commutators where these GIs are commutators, then it follows from the commutator property that this is less than or equal to just ND. But on the other hand, since F is homogeneous, F is unbounded. So okay, yeah, so that's the proof of the corollary. Does it make sense?
What is capital D?
D is this D is this number bounding. So if I have a quasimorphism, then I can take a product and write it as the sum up to an error of D. Okay. So if D is, so more explicitly, let's say D happened to be 1. So if I have an element and my quasimorphism has value 100 on it, then there's no way to write it as a product of 99, of 99 or fewer commutators. Okay. So it's an easy application of our quasimorphisms that the commutator length is unbounded. Another interesting kind of example comes from trying to understand how continuous the commutator length is. This group, it has a natural topology on it coming from the C0 topology. And if I have two group elements that are close in C0, I can ask whether their commutator lengths are close. Well, a related question was studied in the case of surfaces by the same group of authors, Bowden, Hansel, and Webb, except they looked at this stable commutator length. Remember, that's actually the name of Caligari's book. So what the stable commutator length is I take the commutator length of an element, I raise it to the nth power and divide by that. And there's a whole bunch of literature on commutator length. One motivation for studying the stable commutator length is that it's generally easier to compute. It turns out that commutator lengths for a general group, if you give me an element, it can be super hard to compute, but somehow the stable commutator length is easier. Okay, so for this earlier case of homeomorphisms of a surface, this is continuous. But we show with our quasimorphisms that the stable commutator length is actually unbounded on any C0 neighborhood of the identity in this group. So in particular, it's definitely not continuous. So you get some kind of strange, some surprising contrast to the previous result. I probably won't have time to explain much about the proof, although we can see at the end. Are there any questions about any of this stuff? Okay, so for a different kind of application, it's interesting to think about this so-called fragmentation norm. So say I've normalized my sphere to...
For a given element, can you actually approach to 0 by taking the roots of the element? Like, are there roots of the element that allows you to approach to 0?
You mean in our corollary?
Yeah, so you said something for any C0 neighborhood of the identity, but for instance, if you have if an arbitrary element is a power of something in a small neighborhood of the identity, then that just follows, the statement actually follows from the unboundedness of a whole group, right? It's not so important.
Well, no, I mean, I'm not sure I completely understand. so you need, in order for this to, you need, so, okay, so so maybe we discuss a little bit. So you fix the C0 neighborhood of the identity, and now I need something of unbounded stable commutator length. And okay, the commutator length is unbounded, but not necessarily a C0 neighborhood of the identity. I mean, you know, if you,
yeah. But for instance, can I give for a given element? Can I not represent it by something, a power of something in a given C0 neighborhood of the identity? Or?
I see.
And
But then control the CL drops accordingly.
CL drops, but the CCL still stays unbounded. Right?
No, you have, instead of that n g to the n, you have, well,
They're
g to the
constant.
n, and so it drops by factor whatever root you do.
Yeah, but they're still unbounded. Still going to be unbounded.
You could have, say, something which has SCL of, it could be, you could have something which say SCL of 1,000, but then it's only the 1,000th power of the thing whose SCL you're trying to bound in the first place. Yeah. And this, this means the SCL of your 1,000 square root is very small. So.
Okay. Okay, well, maybe we discuss at the end if you want some more. But at any rate, to try to succinctly summarize, another way to think about this is, so the Bowden, Hensel, and Webb, they also have quasimorphisms. But nevertheless, their stable commutator length is C0 continuous, and ours is not. So it's not, this does not follow in some abstract way from just the existence of quasimorphisms. One needs some other fact. Okay, so let's talk about fragmentation norms to give you another idea of something you can do with these quasimorphisms, which is pretty cool. Right, so say I've normalized my sphere to just have area 1. I can ask, if I have a general element, I can ask, how many elements does it take to write it as a product of elements supported on displaceable disks? Okay, so for example, say I fixed an area that's less than 1/2. So then if I have a disk of that area, it's going to be displaceable. And so I fix this area, and I can ask, how many elements does it take to write an arbitrary element G as a product of n elements, each of which are supported on disks of area A? Will in particular be displaceable. It turns out that you can always do this. This is going to be finite for every group element, but we show using our quasimorphisms that this fragmentation norm is again unbounded. So there are elements of this group that are really hard to write as a product of elements that are supported on displaceable disks. And this answers well, maybe a special case of a question of Barago, Ivanov, and Polterovich, who showed the analogous result for the standard tori, but they asked if it holds for complex projective spaces of any dimension. Actually, they were proving it for diffeomorphisms, but so even for diffeomorphisms, this is a new result actually. But it works for homeomorphisms as well. So again, I probably won't have time to say too much about the proof, but it doesn't follow immediately from the existence of a quasimorphism like the argument there. One needs a little bit more. So just to tell you some more things about quasimorphisms. So there's some recent interesting work of Kawamoto, who finds some analogous quasimorphisms to ours for complex quadric hypersurfaces of any dimension. So these are actually the only examples on closed higher dimensional manifolds. So in other words, we found some quasimorphisms on the two-sphere, but in higher dimensions, for diffeomorphisms or for homeomorphisms, for homeomorphisms of the for homeomorphisms of a closed manifold of higher dimensions, Kawamoto's result is sort of the only thing we know. Entov and Polterovich have an analogous result for the 2 n-dimensional ball. I've already mentioned the work of these 3 authors who, if you don't look at some symplectic condition, they find quasimorphisms for just the group of ordinary homeomorphisms and ordinary diffeomorphisms. The 0 just means in the component of the identity. And there's lots of constructions that go back a very long time. So maybe the oldest one that I know of is due to Ruel, who constructed this Ruel invariant. It's a quasimorphism. There are constructions of Entov and Polterovich, Gambadao and Gist, P. There's other works. Quasimorphisms have had a lot of influence in other areas of math, far from symplectic geometry. So here are some examples. Okay. So if there are no questions, oh yeah.
Just for the fragmentation norm, is A something fixed or there exists A such that it can do it?
No, I'm saying you fix any A.
Okay.
Right. You fix an A, but it does have to be less than 1. Any more questions before I move on to the construction of these quasis?
In one sentence, but what was the significance of F supported on each A? Like what was?
Well, so I'm saying, okay, so say you have an arbitrary element, an important technique in this kind of area is the idea of fragmentation. So it might be useful to write it as a product of group elements that are supported on displaceable disks, because I don't know. Then there are things I can do with these disks. This idea is called fragmentation, and so I might want to know then how hard is it to fragment an arbitrary element of my group. And so what I'm saying is there exist elements of this group such that you need arbitrarily large numbers of displaceable disks to write it as a product of elements that are supported on that disk. So it's supposed. So one way to think about it, if you wanted to think about it briefly, is there's this, important technique in surface dynamics called fragmentation, and it's a quantitative measurement of the difficulty of fragmenting a map.
And when you have larger A, then this is not unbounded.
Yeah, I think our proof doesn't. I'd have to think about so we don't show that it's unbounded. I actually don't quite remember whether it's known what happens for larger A or not. Our proof breaks down. Are there more questions? Okay, so now I want to tell you a bit about how to construct these quasimorphisms. And they're constructed, so the point of view that I want to get across is that to construct these kind of quasimorphisms, one wants new invariants of surface maps. And the invariants come from a new construction, or at least a relatively new construction called linked spectral invariants that we carry out in our paper. And so I want to tell you how this construction works. Okay, so just to again clarify what we want to do now, we want invariants of diffeomorphisms of the two-sphere. Now, eventually, we actually want invariants of homeomorphisms of the two-sphere, but the general philosophy here is to first find invariants of diffeomorphisms of the two-sphere, and then show some kind of continuity property to show that they actually give invariants of homeomorphisms of the two-sphere. So my invariants, they live on the space of smooth functions of the two-sphere, and then I want to think of this as parametrizing time. So they're invariants of like Hamiltonians on the two-sphere. Okay. And I'm now going to tell you how you make these things. Just a remark. Okay, so I've stuck to the case of the two-sphere here for 2 reasons. One is expository simplicity. The other is that this quasimorphism question was only asked about the two-sphere anyways. But in our paper, we construct linked spectral invariants for more general surfaces. and also for lots of links using similar methods. And this is actually useful and something we can discuss if I finish early. For example, remember earlier I was saying that the algebraic structure of this group of homeomorphisms of a surface in any genus is somewhat unclear. And you can use these linked spectral invariants to study the group of homeomorphisms of any surface. For example, you can prove a non-simplicity result. You can also prove a kind of Weil law for these linked spectral invariants if you like that sort of thing. But anyways, we just want to stick to quasimorphism. Okay, so let me tell you more about a link spectral invariant. So what is a link? Well, I just want to start with a collection of disjoint circles in my surface. And now I want to define some invariant of a Hamiltonian on the two-sphere coming from a collection like this. So I've drawn for you some particular links. And the strategy is to try to use the so-called construction of Lagrangian spectral invariants. So I put two authors here, Viterbo and O, but the construction also goes back to FO cubed. Later we'll talk about Leclerc and Sapolsky. Okay, so we want to use this Lagrangian spectral invariant construction, but the challenge is that these actual links, individually, each component is actually a displaceable Lagrangian. So normally the Lagrangian spectral invariant construction requires non-vanishing Floer homology. So that's the challenge. There's some previous work that's certainly very relevant to what we do here. Okay, so the two very relevant works are, so first of all, Mack and Smith, they also thought about this issue of how to define a non-vanishing Floer homology for links like this, where each component is displaceable, and they defined a non-vanishing Floer homology. And then Polterovich and Shalukhin addressed how to use this non-vanishing Floer homology to define spectral invariants for links like this. So here's a 4-component link. They have an analog of this for D components for any D. They showed some very interesting applications. Okay, so those are both influential previous works in this area. So our work generalizes the previous works, and it also allows for more general links like this L2. But as I said, also links like this in a surface of arbitrary genus. Okay, so are there any questions about the general setup or the plan of attack? Okay, so again, so the point is each component is displaceable, but I want to try to get some kind of interesting non-vanishing Floer homology. The beautiful idea, so this basic strategy is already in the Mack and Smith paper, but there's a methodological difference that I'll talk about in a little bit. But so the idea, which goes back to this Mack and Smith paper, is to use the link to build a torus in CPD. So in order for this to work, well, I want the torus to actually be monotone. So in order for this to work, the components of the link have to have carefully chosen area. So I've drawn a link for you here. The point is that the area, so there's D components of this link. The areas of each circle is 1 over D plus 1. And then the area of the complement is 1 over D plus 1 as well. So if I take some kind of link like this, then I claim I can build some Lagrangian torus in CPD, and it's actually going to be monotone. Okay, so now how do I get these CDs? Well, now I can use this classical Lagrangian spectral invariant construction. I mean, this is just a monotone Lagrangian torus in CPD, so I can use classical Floer theory. So Leclerc and Sapolsky have written a paper about this that I'll return to relatively soon. FO cubed wrote a paper in a more general setting. And so, yeah, let me say, especially for the specialists, that there is actually an important methodological difference here. We're using the, quote, standard Lagrangian Floer theory, whereas in the previous works, the works by Mack Smith and Polterovich and Shalukhin, they use the so-called orbifold Lagrangian Floer theory. And it's not just a technical difference, it seems to be perhaps important for this application. So I understand, at least I believe I understood from conversations with, for example, Leonid, that it's not clear at all how to see the quasimorphism property that we'll need from the orbifold Lagrangian Floer theory. Yeah, we'll return to maybe why in a bit. Okay, so any questions about any of this?
Yeah, what's the action functional for the Lagrangian or the filtration for the Lagrangian?
We'll get to that.
Oh, okay.
We'll get to that. This is just the general strategy. We'll get to what the action is.
So why do they get to an orbifold setting?
Well, I'm actually not extremely familiar with their method, but I think I'm familiar enough with their method that I can explain where they're in an orbifold setting. However, I'll do it in a couple slides. Okay, so how are we going to build this Lagrangian torus? Well, the idea is to use the symmetric product construction. So, okay, so say I have a link like the one that I drew. As I said, you can do this for a general surface as long as the areas are well chosen. But you can sort of, that's what I mean by equidistributed more or less, but don't worry about that so much. Okay, so what I can do is its product defines just an element in the usual product, then I can take the symmetric product. So this has an action by the symmetric group. I can take its quotient, and what this naturally is a symplectic orbifold, where the singular locus is exactly the diagonal. Okay, so this L1, the product of L1 with LD, was Lagrangian upstairs, so it forms a kind of singular Lagrangian in the quotient. To the extent to which I have an answer for your question, Kai, this would be my answer. That the symmetric product is naturally an orbifold, and I believe that they just work more directly with this as a structure of an orbifold. Now, the link is away from the diagonal, so it's not so bad, but we do something a little bit different. But that might be only a partial answer. I'm not so familiar with exactly what they do. But let me tell you what we do. Okay, so as I was saying, so if I write it like this is an orbifold, and I can think of the natural symplectic form as what you can call a singular current. However, actually, in the case of the two-sphere, this manifold is actually, if I just look at it as a complex manifold, it's actually holomorphic. It's equivalent to CPD, which is a pretty just cool fact. The induced form, the induced structure coming from the symplectic form is going to be singular along the diagonal. Okay, so the perspective that we take is this. There's a nice argument of Perut's, which explains how to modify this structure to get something that's actually a smooth symplectic form, and you just have to modify it in a neighborhood of the diagonal. And in particular, our link, because the components are disjoint, it's away from the diagonal. So what I'm saying is, in our setting, we actually get a symplectic form on this symmetric product, such that the link is a Lagrangian submanifold of that symplectic manifold. Our symplectic form will just be equivalent to the usual Fubini-Studi form on CPD. Are there any questions about that? So at this point, we depart, a fair amount from what was done in the previous works. Okay, so what we prove is that this particular Lagrangian, it's actually monotone, and it has non-vanishing Floer homology. So I'll explain more about why that's true. Okay, so now this gets at Rohill's question about how the spectral invariant works. So, the Floer homology is non-vanishing. So you can use this to define spectral invariants. in the next slide, I'll review how you can define spectral invariance from non-vanishing Lagrangian Floer homology. But first I should explain, what the Hamiltonian is. So remember, I want a rule for taking a function on the surface, a time-varying Hamiltonian on the surface, and producing some kind of a function on the symmetric product. Well, there's an obvious way to do that, which is I can just take my function on the surface and sum up the values of its values on the surface. So I get an induced map on the symmetric product, which I just denote by sim upper D. Okay, and now, as I said, this link is just a monotone torus in CPD. So it has a Lagrangian spectral invariant, I have a function, and I get something associated to any possible class. And so a natural class to take is the fundamental class, and that's my link spectral invariant.
That addition is like actually addition in R, right?
Yeah, that's just actual addition in R.
Wait, could you say again, who is L?
Who is L? Sorry, I just didn't quite hear the question.
Yeah, could you say
What is L? Yeah. Okay, so let me go back. Okay, so this is L. It's a link in my surface. But then, okay, so the link consists of D components. So the Floer homology that we want is so-called sim upper D of L. So what I do is I take my link in my surface, and now this defines a Lagrangian in the symmetric product. The way it works is I just take the product, and then I quotient by the action of the symmetric group, and then I smooth out this. You can think of this as a symplectic current. I smooth it out using this Perutz trick. Maybe don't worry about it so much. This stays Lagrangian, and so so it's just this Lagrangian in the quotient, and that's what I'm calling sim D of L.
I meant you had like, can you move to this next one? Small L, yeah.
This L.
Yeah.
That's just, okay, sorry. That's the Lagrangian spectral invariant. Okay, so what I'm saying is that, okay, so I have this non-vanishing Lagrangian Floer homology. I have a function. I have another slide where I'm going to go through a little bit how Lagrangian spectral invariants work, but let me first try to answer with this slide. So I have a non-vanishing Floer homology. I have a function on this Lagrangian, so I can use that to get a filtration of the Floer homology. There's going to be a spectral invariant associated to any non-zero class in the Floer homology, and I know that this is non-zero. So in particular, the class coming from the fundamental class of the Lagrangian is going to be non-zero. Okay, so L is the spectral invariant associated to that non-zero class. And then CD is just L, but then just normalized by dividing by D. Yeah.
I don't know the degree to which you're going to go into this right now, but so like you have like this obstructed kind of weakly obstructed Lagrangian, right? It has like a bounding cochain.
No, actually, it doesn't have it's unobstructed.
Really?
This Lagrangian is unobstructed. Yeah. For this particular, so it depends on the link.
Yeah.
So we're working with a link that looks like this, which is all you need for a quasimorphism.
Yeah.
If the areas of the link are somewhat different, it might be somewhat obstructed, and you have to use like a bulk deformation. But for this particular link, it's unobstructed. So whether it's going to be obstructed or not depends a bit on the areas here. And even if it's obstructed, it's only you can fix it by just adding I guess the phrase is probably bulk deformation or something. It's not like too badly obstructed.
Totally.
Yeah, you can fix it by adding a multiple of the diagonal.
I see. But for these careful choices of area, it's actually like completely unobstructed. Like you can actually just define.
That's right. Exactly. For this careful choice of areas, it's completely unobstructed. That's right. And by the way, we can't do this for just any link. You don't. We can be a little less careful than this. However, it's not like you can just do whatever you want. If you try to do whatever you want, our methods totally break down. So we have this other parameter eta. If you've read the paper, and if the link is eta monotone, you have to do something to get to deal with the differential. But it's a relatively mild thing, and you're fine. But if the link is just an arbitrary link, our methods don't say anything. Are there more questions while I start? Okay, so yeah, okay, yeah, so especially for non-specialists, if you haven't seen exactly how to even define Lagrangian spectral invariants, and this also gets at Rohill's question, I wanted to sketch a little bit more. You know exactly what this would look like, and there's a great paper about this. It's literally called Spectral Invariants for Monotone Lagrangians by Leclerc and Sapolsky. So you know, you don't have to get into any orbifold kind of stuff or whatever. It's just this nice paper, and we explain in our paper, you know, how to relate to the setup in this paper. But okay, so let me give you a geometric picture, particularly if you've never seen this before. So we have one link L, and we're given some Hamiltonian diffeomorphism of my surface T. Okay, so what this space HF looks like is I look at intersection points between sim D of L and sim D of phi of L. You know, the thing that I get just by pushing the link forward by phi. Okay, but I want to define spectral invariance. So instead of just taking usual intersection points, I take what I would call capped intersection points. I could draw you a picture if you wanted a picture. And okay, so now this is Rohill's question. So I have this, I'm given a Hamiltonian H on the surface, and I can produce a Hamiltonian sim D of H on the symmetric product. And it turns out that that actually gives a filtration on this complex. So now if I have any non-zero class, I can look at the minimum action coming from this filtration to represent it. And then, you know, there's this PSS isomorphism, which allows me to make sense of the spectral invariant coming from the fundamental class of this Lagrangian. Okay, so if you wanted to understand kind of geometrically what's going on here, that's the picture. Are there any questions about that or anything like that?
So the spectral invariants will, in terms of what they represent some kind of like intersection points of these things in your surface, or some kind of collection of intersection points, I guess.
Yeah, so if you're going to draw them, they would be like actions of and you can draw an intersection point between these links as like a Hamiltonian chord going from one component of the link to another.
You're taking any non-zero class where?
Hmm?
I got lost. So you can associate to any non-zero class in what?
Right. Okay. So I take this HF of sim D of L. This is some vector space set.
Okay.
Okay. And it's non-zero. I haven't really explained why it's non-zero. I just stated that it was non-zero. And so if I just take any element of it, it has I can take the minimum action required to represent it. I just put this in quotes, but all I mean by this is that, you know, this is the homology of a chain complex with respect to a differential. So say I pick a non-zero class, it looks like a sum of generators. Each of those have an action, so I can look at the amount of action it was required to do that sum. That would just be the action of the biggest element in that sum. And okay, so then I can look at the most efficient way to do that. And that's the minimum action required to represent it. And I'm calling that so I can do that for any class. It's just convenient to choose this particular class. You know, there's an algebraic structure here such that this is the unit if you prefer to think of it that way. Okay. Great. So are there more questions? I'm very happy to have these questions.
So I think in the paper, what it said specifically was something like, it's the minimum action such that like the quantum cohomology action is non-zero or something if you look below that filtration.
Right.
So I mean, is it clear that that ends up just being the same as this thing you're saying, like this fun, like that if.
Yeah, that's sort of the kind of thing we address in section 7.2.
Okay, so you actually.
We have a section called like spectral invariants are monotone spectral invariants. That's the section.
Oh, right.
But yeah, so you know, to compare with the paper, there's a couple differences with what I'm saying here. One is that, as I say in the paper, we want to handle more general lengths in any surface. Some of this is not so nice. Also, for the method of showing non-vanishing of the Floer homology, you want to do a variation of local system. I've kind of suppressed the local system from the notation here. That's because at the end of the day, you can actually just take the trivial local system. But the method that we use involves variation of local system. And so in the paper, there's a local system written down. But what I've said is actually like a correct definition. Are there more questions while we're stopped? Okay. So, right. So, okay. So remember there were these key facts. I put in the subject line what the key facts are. I said that this, so you get some Lagrangian torus. I said that it's actually monotone, and also that the Floer homology is non-vanishing. Right. Okay. So how do you actually prove this? Well, there's a cool idea for this, which is that our particular Lagrangian torus is actually isotopic to a Clifford torus. So you can, it's actually Hamiltonian isotopic, although we didn't realize it at the time that we wrote the paper. But you can isotope this to just, you know, a standard Clifford torus in CPD. And so you can compare to the situation for the standard Clifford torus. So you get monotonicity this way. Now, okay, how do you show non-vanishing? Well, okay, so I just wrote general theory here. I can elaborate as sort of to some degrees. So it turns out that what you really want to understand are the Maslov index 2 J holomorphic disks with boundaries on, sorry, I should have written SIMD eval. And okay, so the basic idea is that this isotopy induces a cobordism between the corresponding moduli spaces. So in other words, you can just reduce to the case of the Clifford torus, where actually there's already a paper computing the relevant Maslov index 2 disks. So maybe I should elaborate a little bit on general theory. This is where this variation of local systems comes in. I'm not sure I have a pithy two-sentence way to explain it, but there's a standard criteria for non-vanishing of Floer homology coming from, in our setting, what's called the disk potential. So the disk potential is just some way of counting the Maslov index 2 disks going through a marked point. So if you work out the index formula, these are going to have dimension, these are going to live in an n-dimensional moduli space, and my SIMD of L is going to be some n-dimensional Lagrangian torus. And I want to know how many of them there are passing through a marked point on my torus. And then this idea is going back to FO cubed that show that if the count works a nice way, then I get that the Floer homology is zero, at least for some local system. And it turns out when we actually do the calculation that it's non-zero for the trivial local system. So are there general questions about that point?
So they're actual Hamiltonian isotopic.
They're actually Hamiltonian isotopic, although we didn't realize it at the time that we wrote the paper.
Spectral invariants to get out of this are all related by something like conjugation, or like you can change L's and.
Yeah. Yeah. Well, it's a little bit complicated. Maybe I don't know if I want to go that far, but maybe I'll say a little bit at the end about what the spectral invariants that you get out of this are. It's also kind of relevant to something that'll come up in a future slide. Okay, so are there any general questions about this? I actually have some notes more on this disk potential if you want to ask questions about it, but I didn't make a slide about it.
So the thing becomes a Hamiltonian isotropy if you start with the monotone link, right?
Yeah, I'm always just talking about in the setting of our paper, and even
Yeah, so you're always taking monotone thing.
yeah, I mean you can take an eta monotone link
Yeah,
in the setting of our paper, but
yeah. But you need those areas to be the same to get the Hamiltonian.
yeah, I believe that to be the case. Yeah, I mean we didn't even realize there was a Hamiltonian isotopy. It was pointed out to us by Georgios, but we used the fact that there was a totally real isotope.
So in the case of like the other surfaces, I mean, also probably before you realize that there's Hamiltonian isotope. I mean,
Yeah, George.
at some
I think actually Chuck, you realized it independently.
sure.
But anyways,
There's some like direct way of showing direct way of getting the discount just by looking at like the maps to the surface that you get by projecting to certain factors.
yeah, there's this so-called tautological correspondence.
Yeah.
That's right.
But you can also just like on any surface directly check that the disk potential has the necessary properties to define everything, right?
Yeah, for our links, you can just, we have a formula for the disk potential, and then what you really want is you want it to have a critical point.
Yeah.
Okay. And we have a formula in our paper for the disk potential. Are there questions? Okay. Yeah, so I was actually going to give just a sort of general picture. It's a little easier to understand this from the point of view of this tautological correspondence, but let's stick with our link. So maybe one nice way to think about this is, okay, first of all, let's just say on the topological level, you want to know what the set of relative homology classes, rel, this Lagrangian torus in D-eval looks like. So, well, you have these distinguished classes that are bounded by the link, the BIs, and this other class A. And it turns out that these all have Maslov index 2. You get these special classes, and they all have Maslov index 2. And in this case, the disk potential basically just corresponds to. So I was a little vague with what I mean by correspond. It's kind of related to what Julian was saying. But these are basically the relevant disks, the ones that correspond to this picture. Are there questions about that? So in the remaining time, I want to say a little bit about how you prove the quasimorphism property. So what I've done so far is I've just explained how to produce these link spectral invariants. Remember, we wanted to produce quasimorphisms. Okay, so there's a couple ideas here, and I just want to explain them. Okay, so from the previous part of the talk, we have these link spectral invariants. So now to emphasize, these are defined on hand. They're defined for diffeomorphisms, as I defined it. But remember, I said the philosophy is to try to prove some kind of continuity property to get something on continuous maps. So so it turns out actually which is a relatively well-known thing in this area actually, that at least by this point in time, it's by now well known that if I have a particular link spectral invariant, then that's just not going to be C0 continuous. However, if I take a difference of two different ones, then it will extend continuously to this homeomorphism. So basically what I need is I need two different link spectral invariants coming from links with a different number of components. But let me say this a little bit more. Okay, so our quasimorphisms, I'm denoting them by mu sub d instead of c sub d. So, okay, so there's two ideas in the definition of the mu sub d's. The first one is mean normalization. So in the previous part of the talk, I explained how to get invariants of Hamiltonians. Now, if I have a Hamiltonian diffeomorphism, I can try to find a particular I could try to just pick a Hamiltonian that that generates it. That's not a very good idea unless you impose some conditions on the Hamiltonian. So a reasonable condition to impose is what's called mean normalization. So I want the integral of the Hamiltonian to vanish for all times t. So I pick a mean normalized Hamiltonian, and now I homogenize. So that's much like how I define the stable commutator length. So I pick a mean normalized Hamiltonian for phi to the n and divide by n. And so it turns out that this is well defined and it gives a homogeneous quasimorphism. Okay. So I still want to explain, I'm not going to explain why this is well defined, but I do want to explain why it gives a quasimorphism. Are there any questions about the definition?
So because of this Hamiltonian isotropy things that you said before, this mu d's will only depend on d, right?
Yeah, I mean, right. So because of the Hamiltonian isotropy thing I was saying before, that's more like this construction CD of H actually makes sense. I mean, so I guess the way I would say it is in the last part of the talk, I was explaining how to make sense of this CD of H. Now I actually want an invariant of a diffeomorphism, that's this mu d, and then this ends up being a reasonable thing to do. You need some general properties to show that this is well defined, but once you know that so I guess what I would say is that general properties that tend to hold for spectral invariants like this will force this to be well defined. I guess, something else to say maybe more for specialists is even this is actually not quite well defined. In other words, okay, so the basic issue here is that if I have a map instead of a Hamiltonian, okay, I have to understand if I put two different Hamiltonians generating the same time one map into the right-hand side here, are they actually going to give the same link spectral invariant? So I said you can try to mean normalize, but that's actually going to depend on, that's an invariant on ham bar or ham twiddle. On that's only an invariant of the path that you get from the flow. But when you homogenize, you actually get something that depends just on the map in ham. Okay, so maybe the final idea I wanted to explain, and this is where it's useful to work with this classical Lagrangian Floer homology, is to try to understand why is this a quasimorphism? I mean, so I've defined an invariant for you, but it's supposed to have some algebraic properties.
Target HF sim DL dash. Target closed open with HF.
Yeah, sorry. That's right. I wrote the wrong thing. Yeah, so there's a closed open map relating the quantum homology of CPD to the Lagrangian Floer homology. And just from general properties of how this map behaves with respect to action, you get that the spectral invariant associated to the fundamental class on the quantum homology bounds our spectral invariant from above. But on the other hand, if you remember earlier in the talk, I said that Entov and Polterovich had defined quasimorphisms long ago. And in particular, they showed that exactly this construction gives a quasimorphism. So if you take this inequality and you use the fact that this is a quasimorphism, and you just do a little more fiddling, for example, using duality to get a similar lower bound, you get that the right-hand side is a quasimorphism as well. Anyways, this is one place we're working with the so-called classical Lagrangian form homology is helpful. My understanding is that if you work with the orbifold version, it's not so clear that you actually have a closed open map like this. Yeah, so that's how we show that it's a quasimorphism.
The inequality follows from just the fact that the map maps this class to the other class.
Yeah,
And it's action decreasing.
that's right. Yeah, so, well, I think it's 4 o'clock and so, we're basically done.
Sorry, can I see that slide again?
Well, can I just
Sure.
push it to the question and answer? Because I want to finish at 4. So just to finish, okay, so I already said this. Well, I said that the difference of 2 of these is C0 continuous. I didn't give a proof, but at least I think this idea has actually been around for a while, but even we've written a series of papers ourselves, say involving PFH spectral invariants, and we prove a similar fact. So by now, I'd say this is essentially well known. And then, okay, so I actually said that you get an infinite dimensional family, well, to get that infinite dimensional family, with what I've given on the board, you actually don't quite get an infinite dimensional family. I mean, you basically just get a sequence coming from the number of components, but you can vary some of the parameters of the link. That's where you have to think about these eta monotone links. And then you get an infinite dimensional family. And related to showing, in order to show that they're not the same, we would want to discuss how you actually compute these spectral invariants. That's actually sort of a benefit of these spectral invariants, is that they're pretty computable things. But for time reasons, we don't have time to discuss how to compute them. So anyways, that's the end of the talk. Okay, so I owe at least Bareth.
All right, here we go.
Right.
I'm just trying to understand. Okay, you say Entov Polterovich says LSH, LH, left hand side is a quasimorphism.
Yeah, that's right.
This is positive and it's inequality, and that.
Well, and I said you needed a little bit of fiddling. Like for example, it's also true that if I have like F of, and I said, using, I guess I called it Poincare duality, but this is a homogeneous quasimorphism. So it's also true that F of A inverse is negative F of A. So I'm saying if you fiddle with this inequality on some facts like this, you'll eventually come to the conclusion that the right-hand side has to be a quasimorphism as well.
Okay, I see. So I see. It's more okay. It's more like the absolute value of the left-hand side bounds the absolute value, right?
Yeah, right. I mean, what you want is you want to basically like some kind of inequality, like CD of H plus CD of H bar, where this is the thing generating the inverse Hamiltonian. It is bounded by some constant lambda, and then you get, if you can learn that this holds for any Hamiltonian, then you can get that this is a quasimorphism by a little bit of fiddle.
Can I ask a question?
Sure.
Maybe this is a dumb question, but if you have, let's say I didn't take the symmetric product, let's say I just took the product, then all this stuff about the non-displaceability of the Lagrangians just starts to become false, I'm assuming. I mean, there's some necessity of working with the symmetric product because
Well, it's displaceable.
it's displaced. It becomes displaceable, right?
Because if one component is displaceable, you could just displace in that component.
Oh, that's true. Yeah. Okay, no, you're right. Yeah, it was a dumb question. So
No, it's good to ask questions.
yeah.
But what similarly dumb question. What happens when if you literally take the link in the surface and take itself Floer homology? I mean, yeah. So
Like the link itself is not
Yeah.
displaceable, it's a set.
right, the link is not displaceable in the surface.
Yeah, although it's maybe not so clear that the link itself is not displaceable.
Well, I guess.
That,
Well,
I mean, if you
if I stare at
displace it, you have to
it's not
displace
displaceable, right?
the components. That,
Yeah. I think the link is not displaceable.
Yes.
What happens?
What happens with homology for like disjoint unions?
I don't know.
Lagrangian.
I don't know. I don't know what's
Maybe it's just zero.
Is it the direct sum?
Yeah, I don't know.
Right, so sorry, I'm just trying to find a nice picture.
By definition, because the generators are just the sum of all generators.
So
Strips are not changing the components. So.
but I think this is another case where others have maybe answered the question already. But okay, so I think we all agree that certainly each component is displaceable.
Yeah.
And then I think Barris was saying that it's just going to be the direct sum of the components.
I mean, you would definitely have a lot of generators for the picture you had, right? So you're saying like the homology turns out to be zero somehow?
If you take a small enough Hamiltonian, they'll all get displaced.
I don't see how.
no. I think as a link it will have intersections with it. So,
Oh,
Yeah.
Yeah, although, no, so what I was trying to say is it's I mean, I think it follows from the, right, so, well, maybe, why don't you finish what you were saying first? Well, yeah, please.
no, but okay, you say okay.
When you are defining the Floer homology for a link, the generators are the same. It's like the joint union of the generators corresponding to all components. And when you can't
No, but when
Well,
you
it
count
depends. I
intersections.
mean, if you take a small Hamiltonian, then
Yeah, so I mean that
would
no, but like intersection. And the strips will not change the components. So the Floer homology will just
Oh,
define
I
the same.
understand.
just take a small Hamiltonian to displace to compute it. It's not so even so clear that this thing is well defined, right?
Yeah, like is it just?
Is it unobstructed?
Yeah, I don't know.
Also, I think when you pass to symmetric product, you're implicitly actually counting the annuli as well.
That I understand. Yes, I'm still wondering what happens if you don't. But
Wait, what did you say about the annulus? You're saying like if you want to talk about the analog of the disk potential, you have to incorporate annuli also? Is that?
Like the annuli in the sphere correspond to disks in the symmetry sequence.
That's true. Well, are there any other questions? Maybe we'll just continue this discussion offline. All right, if there are no other questions, let's thank speaker again.